Imagine our planet over 4 billion years ago. It was a very different place then. Forget lush forests and sparkling oceans. Early Earth was a violent and chaotic world. Volcanoes erupted across the surface, spewing lava and noxious gases. The atmosphere was thin, offering little protection from the sun's intense radiation. Instead of continents, there were probably just small islands of volcanic rock poking out of a global ocean. Asteroid impacts were frequent, bombarding the planet with immense energy. It was a hostile and unforgiving environment, a far cry from the life-sustaining planet we know today. Yet somehow life emerged from this primordial chaos. It's hard to fathom how anything could survive, let alone thrive in such conditions, but this is where our story begins, with the improbable birth of life on a young and turbulent Earth. It's a story of remarkable resilience, adaptation, and the enduring power of life itself. So how did life arise from this chaotic early Earth? Scientists have pondered this question for centuries, and while we don't have all the answers, we have some intriguing clues. One prevailing theory is the primordial soup hypothesis. Imagine warm, shallow pools of water on early Earth, rich in simple organic molecules like amino acids and sugars. These are the building blocks of life, and scientists believe they could have formed spontaneously in the early Earth's atmosphere. With energy from lightning strikes or the sun's ultraviolet rays, these molecules could have linked together, forming more complex structures like proteins and nucleic acids, the precursors to life. Over time, this soup of organic molecules could have become more concentrated, creating an environment where life could emerge. While the exact details are still debated, the primordial soup hypothesis offers a compelling explanation for how the basic ingredients of life might have arisen on early Earth. While the primordial soup is a popular theory, it's not the only one. Some scientists believe life may have originated in a completely different environment, deep beneath the ocean's surface, near hydrothermal vents. These vents are like underwater geysers, spewing hot, mineral-rich fluids from the Earth's interior. They create unique ecosystems, teeming with life even in the absence of sunlight. The chemicals pouring from these vents, such as hydrogen sulfide and methane, could have provided the energy needed for the first life forms to evolve. The extreme conditions around hydrothermal vents may seem inhospitable, but they could have provided the perfect crucible for life's beginnings. The constant flow of energy and nutrients, combined with protection from the harsh surface environment, makes hydrothermal vents a compelling alternative setting for the origin of life. Regardless of where life began, the first life forms were likely simple single-celled organisms called prokaryotes. These microscopic pioneers were radically different from the plants and animals we see today. They lacked a nucleus, the membrane-bound compartment that houses DNA and more complex cells. Yet these seemingly simple organisms possessed the remarkable ability to replicate themselves, passing on their genetic information to future generations. This ability to reproduce and evolve is the hallmark of life, and it set the stage for the incredible diversity of life we see today. Prokaryotes thrived in the early Earth's oceans, their populations expanding and diversifying over millions of years. They were the dominant form of life for billions of years, shaping the planet in ways we are only beginning to understand. Section 5. Living fossils, stromatolites, and the rise of oxygen. As prokaryotes flourished, some species developed a remarkable ability, photosynthesis. Just like plants today, these photosynthetic prokaryotes, known as cyanobacteria, could harness the sun's energy to convert carbon dioxide and water into sugars, releasing oxygen as a byproduct. This newfound ability had a profound impact on the planet. Over time, oxygen, once a scarce gas in the atmosphere, began to accumulate. Evidence of this early oxygen production can be found in stromatolites, layered structures formed by colonies of cyanobacteria. Stromatolites are among the oldest fossils on Earth, some dating back over 3.5 billion years. These living fossils provide a glimpse into a time when life was transforming the planet, paving the way for the evolution of oxygen-breathing organisms like ourselves. Section 6. The Great Oxidation Event, a turning point in life's story. The gradual buildup of oxygen in the atmosphere, driven by cyanobacteria, eventually reached a tipping point. Around 2.4 billion years ago, oxygen levels surged dramatically in what is known as the Great Oxidation Event. This event was a turning point in the history of life. While oxygen was essential for the evolution of many life forms, it was toxic to many anaerobic organisms that had thrived in the oxygen-poor early Earth. The Great Oxidation Event led to a mass extinction, wiping out many anaerobic life forms. However, this event also paved the way for the evolution of new oxygen-breathing life forms. The stage was set for the rise of more complex cells and eventually the incredible diversity of plants and animals we see today. Section 7, From Simplicity to Complexity, the Long Road Ahead. The emergence of life from non-living matter, a process known as abiogenesis, remains one of the most profound mysteries in science. While we have made significant strides in understanding the conditions on early Earth and the potential pathways for life's emergence, the exact details remain elusive. The journey from those first simple prokaryotes to the complex life forms we see today was long and arduous, spanning billions of years and countless evolutionary leaps. It involved the development of eukaryotic cells, cells with a nucleus and other complex structures, which eventually gave rise to multicellular organisms. The story of life on Earth is one of constant change, adaptation, and incredible resilience. It's a story that continues to unfold today, with each new scientific discovery shedding light on our planet's remarkable past. Section 8. Searching for Origins, the Ongoing Quest. The search for life's origins is a global endeavor, with scientists from various disciplines, biologists, chemists, geologists, astronomers contributing to this grand puzzle. From recreating the conditions of early Earth in laboratories to exploring extreme environments like hydrothermal vents and ancient rock formations, researchers are piecing together the clues of our planet's earliest history. One promising avenue of research involves studying the genetic makeup of modern organisms. By comparing the genes of different species, scientists can trace their evolutionary relationships and potentially identify common ancestors, including those of the earliest life forms. The quest to understand our origins is not merely an academic exercise. It has profound implications for our understanding of life itself and our place in the universe. Section 9. The Cosmic Perspective, Life Beyond Earth. The discovery of life beyond Earth, even microbial life, would be one of the most significant discoveries in human history. It would revolutionize our understanding of life's place in the universe and raise profound questions about the nature of existence. While we have yet to find definitive evidence of extraterrestrial life, the search is well underway. Spacecraft and telescopes are scanning the cosmos for signs of habitable planets and potential biosignatures, chemical or physical markers that might indicate the presence of life. The vastness of the universe suggests that life in some form may exist elsewhere. The conditions that gave rise to life on Earth, while seemingly unique, may have been replicated on countless other planets throughout the cosmos. The search for life beyond Earth is a testament to our innate curiosity and our desire to understand our place in the grand scheme of things. Section 10. A Legacy of Life, Our Connection to the Early Earth. As we delve deeper into the mysteries of life's origins, we gain a profound appreciation for the interconnectedness of all living things. We are all descendants of those first simple life forms that emerged on early Earth billions of years ago. The air we breathe, the food we eat, the very building blocks of our bodies, all can be traced back to those early pioneers. Their legacy is woven into the fabric of our planet, from the oxygen-rich atmosphere we depend on to the fossil fuels that power our modern world. Understanding our connection to the early Earth not only satisfies our scientific curiosity, but also instills a sense of responsibility for the future of life on our planet. As we continue to explore the mysteries of our origins, we embark on a journey of self-discovery, one that connects us to the vast history of life on Earth and reminds us of the preciousness and fragility of our planet.